तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
What we have seen in the previous lectures was how to calculate the Fourier coefficients of a given periodic waveform, and through an example we saw how this information could be utilized to assess the steady state performance of an electrical network excited by periodic non-sinusoidal sources. Today we'll take up the concept of frequency spectra. To introduce this, let us consider the statement of a periodic function of time. Suppose I describe the periodic function of time as follows. Period is T0 and Ft equals A for t ranging from 0 to T0 upon 2 and minus A for t ranging from T0 by 2 to T0. This is a complete description of the periodic function, but this is just a cold statement of facts. On the other hand, if I picture this information in the form of a waveform, then the whole situation comes alive. So if you plot this for a whole period, you have this and repeats itself endlessly in both directions. This is A, this is minus A, 0, T0 upon 2, T0, and this is of T. So information about the periodic waveform presented in this manner gives you a real feel for the variation, and it is often useful therefore for us to plot these functions of time through waveforms like this. We know this is called a waveform. And that is the reason why an oscilloscope is such a useful instrument in the laboratory, because we can see the variations with respect to time which are often masked in an analytical expression of this type. Now, when you perform the Fourier analysis of this, we can describe the Fourier coefficients of this waveform. We know that Cn, the Fourier coefficient in the exponential representation, is minus j 2a by n pi. You recall that in the trigonometric expansion of this function of time, the coefficients of sin n omega naught t is 4a by n pi, and since Cn is an minus j bn by 2, bn terms are only present 4a by n pi for odd n, therefore Cn will be minus j 2a by n pi for odd n and 0 for even n. Now this statement again gives you the complete picture, but there is nothing like representing them in the form of a figure. So suppose we want to do a similar operation like this with respect to functions of time. So we should be able to plot Cn for different values of n in the form of a graph or a figure. But then there is a problem. Cn is a complex number. So if we have to indicate a complex number, we have to indicate both its magnitude and phase. There are two parameters associated with each value of Cn. Therefore, a convenient way of doing this would be to plot the magnitudes of Cn for different values of n, and the angle associated with Pn, with angle associated with Cn, which we call Pn, for different values of n. So in this case, we can graduate the x-axis in terms of n or omega naught. Suppose we do it in terms of n, 0, 1, 2, 3, 4, 5, etc. And on the negative side, minus 1, minus 2, minus 3, minus 4, minus 5, etc. So when you plot the magnitude of Cn, then you have, there is no DC term, there is one component here, another component here, third component here. This is even harmonics are absent, therefore that will be how it looks like. And phase, every non-vanishing Cn will have minus 90 degrees, as you can see here. Therefore, and since for minus n it's the conjugate, you have plus p by 2. Minus pi by 2. You can graduate this x-axis not necessarily in terms of n, we can as well do it in terms of frequency or angular frequency. So I can write this as 0, omega naught, 2 omega naught, 3 omega naught, and 4 omega naught, 5 omega naught, etc. The point to note is that this is what is called a line spectrum. This such a representation is called a spectrum. This is called the magnitude spectrum. And this is called the phase spectrum. And together they go by the name spectra, the magnitude and phase spectra. One point we should note is that as long as the function is periodic, that is the type of functions we are dealing with at this stage, the spectrum consists of components only at the DC and possible integral multiples of the fundamental frequency. There cannot be any term in between. So these are called line spectra. Both this magnitude and phase spectra are now for a periodic situation are line spectra. And the spacing between two adjacent components, this is also a component but 0 magnitude, the spacing between two adjacent components is omega naught if you graduate this in terms of frequency. So the entire information regarding Cn can be pictorially represented in this fashion. It gives you in a graphic way what are the frequency components present and what are the relative sizes. All this information is given in a pictorial representation like this. Therefore, it is often convenient and useful for us to plot the spectra of periodic waveforms in this fashion. For example, you draw an envelope like this, you can say this is how various Fourier coefficients decay for large values of m. So generalizing this, we can say now that for periodic waveforms we have two kinds of spectra, the magnitude spectrum which is really a plot of the magnitude Cn as a function of n or omega naught or omega, and so in general you have values for integral values of n or integral multiples of omega naught. You may be a little puzzled about this meaning of minus omega naught. What is the negative frequency? It is just the coefficient of the term t in the exponential representation. You write minus j omega naught t. It has the dimensions of frequency. As I mentioned earlier, these two together constitute a sinusoid of frequency omega naught. So this is only a mathematical terminology that we use, and we should leave it at that. We should not try to find out a physical meaning for minus omega naught as a frequency. If you plot the phase spectrum, in general again you have some values. This is the angle of Cn, which is equal to Pn. The phase spectrum turns out to be an odd function of n. Why? Because we observed earlier that Cn, C minus n is Cn conjugate, which means that the angle associated with Cn and the angle associated with Cf minus n are the negatives of each other. Therefore, if for n equals 2 it has a certain phase angle, n equals minus 2 it is exactly the negative. So the phase spectrum is an odd function of n. On the other hand, the magnitude spectrum, which is the magnitude of Cn, is an even function because the magnitude of C minus n is the same as the magnitude of Cn. So a magnitude spectrum is an even function of n. This is an odd function of n. So these are two important properties of the spectra. The magnitude spectrum is an even function of n, the phase spectrum is an odd function of n. And it is conventional to plot the spectra for both the positive and negative indices n, even though, as you can see, if we give this information pertaining to positive n for Cn and positive n for Pn, we can reproduce what is happening on the negative side utilizing the property of evenness for the magnitude and odd for recognizing that Pn is an odd function of n. It is also sometimes this is also done. Instead of plotting Cn, one plots square root of an squared plus bn squared, this being the amplitude of the nth harmonic component. You recall that in the trigonometric expansion of a function of time, we can the amplitude of the nth harmonic is square root of an squared plus bn squared, and this is the coefficient of cos n omega naught t plus phi n function of time. So this can be plotted also 0, 1, 2, 3, 4, etc. This is a single sided sometimes called amplitude spectrum. Because what we are really plotting is the coefficient in the you recall that the nth harmonic is represented by cos n omega naught t. So we are plotting this. There's an alternative. So instead of this magnitude spectrum, one can plot this, but in this case we only have a positive non-negative values of n to deal with, therefore this turns out to be a single-sided amplitude spectrum. This is an alternative way of plotting the magnitude spectrum, nothing more than this. However, we normally confine our work to utilizing plotting the spectra in this manner rather than in this manner, because that will be convenient for us when we go to the Fourier integral concept. You notice that if this is C0, this is C1, this is C2, when you go to the amplitude spectrum, square root of an squared plus bn squared, as you know, is 2 times C of n. Therefore, this will be 2C1, 2C2, 2C3, etc. But the DC term will be the same, that is C0. Okay, so the concept of spectra is just a way of indicating the various harmonic coefficients in a pictorial way, and since each harmonic coefficient is associated with two quantities, either an or bn, or magnitude of Cn and phase of Cn. For example, if you choose to plot in this fashion, the angle information is again once again this. So as far as the phase spectrum is concerned, you don't have any alternative. On the other hand, if you like, you can plot an and bn separately, but that is an unconventional way of doing it. So since each Fourier coefficient is specified by two parameters, we need to have two spectra, and usually we do this in the form of a magnitude spectrum and a phase spectrum. Now let us use this, with this background, let us plot the spectra of a few representative waveforms. I would like to keep this waveform, and this is the spectra. So let me see suppose I take a waveform which is related to this, in the sense that it is a square wave, all right, but shifted from the square wave that we have already dealt with. This will be 3 T naught upon 4. This is minus T naught upon 4. Let me call this F2 of T if the original square wave that we have is F1 of T. That means for F1 of T, I am considering this to be F1 of T. Right. We know that this leads to a Fourier coefficient, let us say Cn1, because I am calling this F1, minus J2a by n pi, minus J2a by n pi. Now what would be the Fourier coefficient for this? You recall, you can say from this, these two are essentially the same waveforms except for a shift in the origin. In fact, f of 2 of t is obtained by advancing this by a quarter period. Suppose similar events are made to occur t naught by 4 seconds earlier, then this waveform is obtained from that. So a rise from a negative a to plus a occurs at 0, now that occurs at t naught by 4 seconds earlier. Therefore, f2 of t can be written as f1 of t plus t naught upon 4. So the whole thing is advanced by t naught by 4 seconds. Cn2 the Fourier coefficient for f2 of t will therefore be 1 over t naught 0 to t naught f2 of t, which is f1, t plus t naught upon 4 e power minus j n omega naught t dt. Now, in order to relate Cn2 with Cn1, let us make the identification that t plus t naught upon 4 equals x, in which case we can express this as 1 over t naught. Now, substitute the variable t by the variable x, dt will be dx, and this will be f1 of x, of course, and e power minus jn omega naught t will be x minus t naught upon 4. And the limits of integration, when t equals 0, x will be t naught upon 4, and when x is t naught, this will be 5 t naught upon 4, x will be 5 t naught upon 4. And therefore, this will now be equal to 1 over t naught upon 4 to 5 t naught upon 4 f1 of x. I can write this as minus jn omega naught x dx, and the whole thing multiplied by a constant e jn omega naught t naught upon 4. E jn omega naught t naught upon 4 is of course e power jn pi upon 2, because omega naught t naught equals n pi upon 2. So, this will now become this multiplied by e power jn pi by 2. After all, x is a dummy variable here, you can go back to t, this was f1 of t times e power minus jn omega naught t dt. This is exactly the formula for evaluating Cn1, because we are integrating this over a complete period. Therefore, this will become Cn1 multiplied by e power jn pi upon 2. So, e power jn pi by 2 has a magnitude 1, and its angle of course depends upon the value of n. So, Cn2 happens to be equal to Cn1 e power jn pi by 2. The Fourier coefficients for this Cn2 is Cn1 e to the power of j n pi upon 2. So, what is the spectrum of this? How does it look like? The magnitude spectrum will be the same as that of Cn1. Why? Because the magnitude of Cn2 is the same as magnitude of Cn1, because the magnitude of this is 1. So, you have one, 3, 5, 1, 3, 5. So, this will be 2a by pi, 2a by 3 pi, 2a by 5 pi, etc. So, the magnitude spectrum remains unchanged. Same magnitude spectrum as that of f1 of t. So, this magnitude spectrum and that will be identical. Phase, however, gets modified. So, instead of this phase, you have at each component you have an addition of n times pi upon 2. DC, of course, there is nothing. At 1, it is minus pi upon 2. So, add to that another pi upon 2. So, this becomes 0. At 2, there is no component to deal with. At 3, it is minus pi upon 2. to that you add 3 pi upon 2. So that becomes 180 degrees. You can as well say it is minus pi, plus pi or minus pi are one and the same. And at 5, you add 5 pi upon 2, it's already pi upon 2, minus pi upon 2, you add 5 pi upon 2, it becomes 2 pi, once again it is 0. So you have a whole series of angles 0 or pi alternately, and this is the phase spectrum. So the conclusion that we draw from this is, if we have a square wave, whether you put the origin here or origin somewhere here, the magnitude spectrum will remain the same. So if you have a periodic function, the amplitudes of different harmonics or the ratio of the amplitudes of different harmonics will remain the same irrespective of where you pitch your origin, because that is a fundamental property of the waveform, how different harmonics can go together to compose the given wave. So the magnitude spectrum remains invariant under translation in respect to time, but the phase spectrum undergoes a change depending upon where you put the origin. Usually we are interested only in the magnitude spectrum because we would like to know the relative proportions of the various harmonic components, and therefore we can say that the magnitude spectrum is invariant under the operation of shift in the time axis. Let us take a second example. Suppose the periodic function that we are talking about is one which is a periodic impulse train. So each is of an impulse delta function of unit magnitude, unit strength, so f of t is a periodic waveform with one impulse sitting in each period at the center. So we can write formally that f of t consists of a number of impulses delta t minus n t naught, n going from minus infinity to plus infinity. So for each value of n there is an impulse. At 0 this is the impulse, when n equals 1 this is after all delta t minus t naught, and this is delta t minus 2 t naught, and so on. So all these impulses go together to constitute this f of t. Now what is the Fourier spectrum for this? So you have to find out the Fourier coefficients to start with, and this can be done with surprising ease, because whenever we have impulses inside the integration sign, then the integration becomes quite simple, as we had already seen. So Cn here will be 1 over t naught say minus t naught upon 2 to plus t naught upon 2. So inside this range, function that we have got is only delta t e to the power of minus jn omega naught dt. Now what is the result of this integration? Whenever a delta t multiplies a certain function of time and you integrate over an interval which contains that impulse, the value is simply the value of this function at t equals 0, because the impulse is sitting at t equals 0. Therefore the value of this function is 1, value of this simply this quantity evaluated at t equals 0, and that of course is 1. Therefore Cn naught is 1 upon t naught. Normally when we evaluate the Fourier coefficients, it would be advisable for us to verify if the general expression for Cn is also valid for n equals 0. So if you want to do it independently, this is 1 over t naught, say minus t naught upon 2 to t naught upon 2, delta t dt. Certainly this is equal to 1, therefore this is 1 over t naught. So what do we have for the spectrum? We have Cn magnitude spectrum, flat, all components are the same value 1 over t naught. Phase 0, because C naught is 0, that means phase spectrum. Very interesting result that we got now. You have a train of impulses of unit strength occurring regularly at intervals of t naught, then the spectrum for that is all flat here, in the sense that all harmonic components have the same magnitude. They don't go down as n goes up, they retain. That means all frequencies, that means we can say a train of impulses is, so to say, impartial to the order of the harmonic. All harmonics of equal strength go together to compose this impulse train. This is quite an important fact which will occur. This particular property occurs again and again in our future discussions. So we observe that if f of t is equal to this train of impulses, the Fourier series expansion for this is 1 over t naught e to the power of j n omega naught t, n ranging from minus infinity to plus infinity. So this is a result which is a very compact and has a nice look about it. You have summation from minus infinity to plus infinity of whole of these impulses. On the other side, you have summation from minus infinity to plus infinity of exponential terms. So the spectra gives us an indication how the various coefficients go up or remain the same. You have taken one extreme example of a situation where the spectra magnitude remains constant right through. Okay. So with this background, let us go further and construct another spectrum. As a third example of finding out the spectra, let us consider a periodic pulse train with a waveform depicted as here, where a rectangular pulse repeats itself for every t naught seconds. The pulse has a width d and an amplitude a, and it is centered symmetrically with respect to the origin. So this is a periodic pulse train, and the duty cycle is d upon t. That is, for t naught it lasts only for d seconds. So Cn for this will be 1 over t naught minus t naught upon 2 to plus t naught upon 2 f of t e to the power of minus j n omega naught t dt. This is the standard formula. But in our particular case, this f of t lasts only from minus d upon 2 to plus d upon 2, and the rest of the period it is 0. Therefore, we can write this as minus d upon 2 to plus d upon 2, and in this interval its value is a to the a times e to the power of minus j n omega naught t dt. And this can be written as a minus j n omega naught t naught e to the power of minus j n omega naught t, that is evaluated between the limits minus d upon 2 to plus d upon 2. A minus j n omega naught t naught e to the power of minus j n omega naught d upon 2 minus e to the power of j n omega naught d upon 2. substituting the lower limit minus d upon 2. So if you pick up from here and go here, Cm will now be A divided by minus Jn omega naught T naught. This you notice, if we had reversed the sign, e to the power of Jn omega naught d upon 2 minus e to the power of minus Jn omega naught d upon 2 would be 2j sin n omega naught d upon 2. But since the negative sign, we reverse this thing, I can write this as minus 2j sin n omega naught d upon 2. So cancelling this minus j right, both sides, you have 2a n omega naught t naught sin n omega naught t upon 2. I will write this in a slightly different fashion. Suppose I write this sin n omega naught d upon 2, I establish a denominator n omega naught d upon 2. So this 2 is taken over here, so a remains, and since I introduced a d in the denominator, I put a d in the numerator. N omega naught are already carried over here, so all that remains is this. I put this in this particular form because this function we have is at the form sin theta by theta, which is a function which is well known in mathematics literature and which comes up quite frequently in waveforms of this sort. So to plot this spectrum corresponding to this, let us fill ourselves up on some background information of the variation of sin theta by theta. So if we are having a function sin theta by theta, this is, if you take theta, this, what we are interested in is to find out the variation of sin theta by theta. So let us plot this is sin theta and theta will be like this. So we are dividing this waveform by this. So we can see that as the theta increases, the amplitude of the oscillations decreases. On the other hand, at theta equals 0, this is 0 by 0. So if you take sin theta by theta, evaluating at theta equals 0, we have to take the limit as theta goes to 0. That means you have to take the derivative d by d theta of sin theta in the numerator, d by d theta of theta in the denominator, and evaluate at t equals 0 using the L'Hopital's rule, and that turns out to be 1. So when you divide this quantity by this, you get sin theta by theta curve. It starts with 1 and will now exhibit oscillations with the decreasing amplitudes. And since this is an even function of theta, both the numerator and denominator are odd functions, therefore the ratio is even function, so you get something like this. This is the variation of sin theta by theta. This function occurs again and again in Fourier theory, so we would like to see the properties of this. So at theta equals 0, it is 1. And it becomes 0 again at pi, 2 pi, 3 pi, and so on and so forth. Again on the negative side, minus pi, minus 2 pi. So this is the type of function that we have got. However, we don't have continuous variation of theta. We are interested in finding out the values of this at specific values of theta, which are given by integral values of m. So consequently, the spectrum of this would be magnitude. We have an envelope like this because we are considering only the magnitude. So the negative loops are flipped over, this will be the envelope of your shear magnitude, but the lines you will have only components like this at specific values of integral values of m, 0, 1, 2, etc. In particular, C0 will be AD upon T. As you can see, the average over a complete period is AD upon T naught. So that is the DC value, AD upon T naught, and like this it will go. So the spectrum of a periodic pulse time will have this type of character, and since this is a real quantity, as far the phase is concerned, we can say it is either 0 or pi, and sometimes when the Cn quantity turns out to be real, we can plot Cn simply as like this. So we don't have to plot the magnitude and phase spectra separately. So Cn is real, is either positive or negative, and so that information can be given. Since Cn is real, phase spectrum is not necessary. Phase spectrum need not be separately plotted. So the amplitudes go down in this fashion. We have seen in one of the earlier examples that when you have impulse functions, the evaluation of Fourier coefficients becomes quite simple because integration with impulses is easy. So I would like to take up an example where we make use of the impulses in the evaluation of Fourier coefficients. Let us take a triangular wave like this, and suppose I call this f of t, and let its Fourier expansion be Jn omega naught t, n from minus infinity to plus infinity. To evaluate the Cn in this for this waveform requires good amount of computational effort. But let us see what happens if you take the derivative of this, which is this. If you take the derivative of this, the slope here is constant, but negative, therefore it's like this. So if you take the derivative of f t, it results in a square wave like this, f prime t. But we won't stop that. We will take the second derivative of this. The derivative of this now, as you can see, it is 0 everywhere except where there is a discontinuity. Therefore, there is an impulse here and an impulse here. And what are the magnitudes of these impulses? The slope here is, it ranges by an amount 2a in t naught by 2. Therefore, it is 4a by t naught. That is the magnitude here, and this minus 4a by t naught. Therefore, the jump that is involved in going from minus 4a upon t naught to plus 4a upon t naught is 8a upon t naught. Therefore, there are two impulses here, one positive and the other negative, with strengths equal to 8a upon t naught. And suppose we find the Fourier coefficients for this periodic waveform, then can we relate those Fourier coefficients, the Fourier coefficients of the parent waveform? That's what we want to do. So if f t has this Fourier series, f prime t, assuming that we can differentiate under the summation sign, this will be Cn Jn omega naught e to the power of Jn omega naught t. If you differentiate again, it will be Cn, again derivative of this. So you multiply with another Jn omega naught, so it will be n squared omega naught squared e to the power of Jn omega naught. Let us call this Dn. Let us call this Fourier coefficient for this to be Dn. N from minus infinity to plus infinity of Dn e to the power of Jn omega naught t. So if you calculate Dn for this periodic function having impulses, then we know Dn and Cn are related by this Cn squared, Cn times minus n squared omega naught squared is Dn. So that is the plan of action. we will find out the Fourier coefficients for dn and then find out from that Cn. So dn is 1 upon T naught from minus T naught upon 2 to plus T naught upon 2. In this range of integration, we have two delta functions. So one delta function at both magnitudes 8a upon T naught, delta T plus T naught upon 4, that is this delta here at negative values of time, and another delta function at T naught upon 4 with a negative sign, therefore minus delta T minus T naught upon 4 e to the power of minus j n omega naught t dt. So we have got 8a upon T naught squared. Now this delta multiplied by this is being integrated, therefore this will be e to the power of minus j n omega naught minus T naught upon 4, evaluated it when T equals minus T naught upon 4, that means plus T naught upon 4, minus e to the power of minus j n omega naught T naught upon 4. And you can carry this out. Finally, you can show that is j16 a upon T naught squared sin n pi by 2 r. This is your dn, therefore Cn will be obtained by dividing dn by minus n squared omega naught squared. So G16a minus omega naught squared n squared T naught squared sin n pi by 2, and you can complete the work and can show that this will turn out to be minus j 4a by pi squared n squared minus 1 raised to the power of n minus 1 by 2 for odd n and 0 for even n. So that is the Fourier coefficients for the original triangular waveform. Recognizing that Cn equals an minus jbn by 2, you can write this contains bn is 8a by pi squared n squared minus 1 n upon 2 for odd n, and we know an is 0, bn is 0 for even n, and what about C naught? C naught has to be separately evaluated. I will explain in a moment. C naught for this waveform, because it is a 0 average from the original waveform, C naught is 0. Other Cn have already been obtained. So the finally f of t will be 8a by pi squared sin omega naught t minus 8a by 9 pi squared sin 3 omega naught t, etc., etc. Now let us see what happens. If you have a constant term here, when you take the derivative, that constant term disappears. Therefore, a DC term gets lost here, and therefore you can't expect to get that term to be present here. So the DC term in the original function has to be separately evaluated, because that information is lost when you go to this, right? So C naught in this case has to be separately evaluated. You can't obtain from this information. Now what other terms can possibly get lost? If there is a constant term here, that can get lost when you take the derivative. But a constant term here means that you have a term like kt here. Unless there is a term like kt, you can't get a constant term in the derivative. And if you have a term like kt in a periodic function, that completely spoils the periodicity of the function. Therefore, if it is a periodic function, you can't have a kt term here, so you can't have a constant term here as a derivative of this. Therefore, there is no trouble on that score. The only trouble can come because the C naught that is here can get lost, and that has to be separately evaluated, and in this case the constant term is 0. So this example illustrates how the Fourier coefficients can sometimes be evaluated by taking the first or second derivative as the case may be, and making use of a function which has only impulses as illustrated here. So in this lecture, what we have done is we have introduced ourselves to the concept of frequency spectra, in particular the magnitude and phase spectra associated with the Cn coefficients. We observed that these both are line spectra. The magnitude spectrum is an even function of n, and this phase spectrum is an odd function of n. And we have, through a series of examples, we saw how the spectra can be constructed. In particular, we have constructed the spectra of a train of impulses, the square wave, and a train of pulses. And also we saw how the facility provided by impulses in the integration procedures can be availed of in situations where either the first derivative or the second derivative, as this case, contains entirely impulses. In that case, it would pay us to take the derivative and find out the Fourier series for that, and use that information to find out the Fourier series of the original waveform as done in this case.